polynomial functions. So when you're in a family with someone, you have similar traits to them typically. So we're finding out what characteristics among polynomial functions would put two different polynomial functions in the same family. So the first definition that we go with, first note that we go with is a definition on a family of polynomial functions. And we can say that a family of polynomial functions is a set of functions. So it's more than one, it's a group of functions with the same zeros. So a family of polynomial functions is a set of functions with the same zeros. New line. The graphs of, let's simplify, the graphs of these have the same x-intercepts. If zeros correspond with the x-intercepts of the graph, then they have the same zeros. That means they'll have the same x-intercepts, but have different y-intercepts. If they had the same x-intercepts and y-intercept, they would be the same graph. And this is only not true. So unless 0 is one of the x-ints, because then it would go through 0, 0, and all of the other members of the family would then also have an x-intercept at 0, which would be at 0, 0. So they have the same x-intercepts, but a different y-intercept. They have the same roots, okay? An equation for the family of polynomial functions, an equation for the family of polynomial functions with zeros at a1, a2, a3, ... So we're speaking in general terms. These are the zeros. X equals this, x equals that, x equals the next one, all the way to the last 0, which would be a sub n. Now, it doesn't need to have a ton of zeros. It could have 2 zeros. It could have 1 0, as long as it fulfills this requirement that they have the same x-intercepts. They have the same zeros. Okay? It could be a polynomial equation to the 10th degree, as long as it has all the same zeros in it. Well, the zeros correspond to the factors inside of a polynomial function. So if they have the same zeros, then that means they have the same binomial factors inside the function. So an equation with zeros of this is, and I'll write it on the next line, y equals k times x minus a1, x minus a2, on and on and on and on, till you get down to the last factor. And what has to be true of this, where k belongs to the set of real numbers and k cannot equal 0. Okay, so it has all the same factors. We'll know what all of these numbers are. X minus something, x minus something, x minus something, all the way throughout once we have a factored form of this polynomial function, and the factors correspond to the zeros. And out in front you have a multiplier. So it might be, you know, it might be a shallow little thing, or it might stretch, okay? If this was the x-axis, then these two graphs would be in the same family, but they'd have a different value of k, but they would have all the same factors to get all the same zeros. So in example 1, we're asked to represent a family of functions algebraically, and they give us what type of function it is. It is a quadratic function, so there will be 2 factors of x, and we're told that the zeros are at 2 and negative 3. We're told that the zeros are at 2 and negative 3. Example 1, our zeros at 2 and negative 3. So from that, we can determine what the factors are. So if those are the zeros, then our factors are x minus 2 and x plus 3, okay? The general form is right here for us. X minus a1, which is the first 0. So here we have x minus 2. And then x minus negative 3 becomes x plus 3. From there, we can just put it right into our equation. The equation for this family is y equals some multiplier k, and the factors are x minus 2, x plus 3. That's step A. In B, we're asked to write equations for 2 functions that belong to this family. Well, all we have to do, we know the factors. You could put in any value of k at all. So if we do 2, let's just say for k equals 3, we would end up with y equals 3 times x minus 2 times x plus 3. And you could choose any other value of, you could choose k equals negative 1/4. And then y would equal negative 1/4 times x minus 2 times x plus 3. And you could think about what these transformations would do to the graph, these values of k. I mean, the negative 1 will flip it. The 3 will stretch it. The 1/4 will compress it. But all along, it will still go through the points 2 and negative 3. C. Determine an equation for the member of the family that passes through the point 1, 4. So when you get to something like this, through 1, 4, what you have to understand is that there is only one possible function for a curve that is part of this family and goes through a set point. Okay, you can think back to when we dealt with lines. There's only one line in the whole world that goes through this point and this point. Okay, so just the same way, there's only one curve in the whole world that goes through these x-intercepts and goes through this point. Okay, if this point moved anywhere else, like here or here or here, it would be a different curve altogether. Okay, so now there's only one possible solution. What do? Well, we take our function, our family, which is y equals k x minus 2 x plus 3, and we know that the point 1, 4 is on the curve, which means the coordinates x equals 1, y equals 4 will satisfy the equation. Hopefully you are familiar with that language still. So all we need to do to find k is fill in the points, sub in the points that the coordinates that satisfy the equation. So y is 4. We don't know k, but we know in this case x is 1 and x is 1. So we fill that in. Now we have one equation, and the only thing missing is k. So on the left side we still have 4 times k. In the first bracket we have negative 1. Second bracket we have 4. That's 4 equals negative 4 times k. Divide both sides by negative 4, you get k equals negative 1. Therefore, the function that goes through the point 1, 4 and is still part of this family has a multiplier of -1. So you can just put a negative sign out there and copy down your factors, x minus 2, x plus 3. All right, so we used the zeros to develop the factors. We used the factors to develop an equation for the family of polynomial functions. We developed a list. You could go on forever and ever, a list of polynomial functions that actually are part of that family. And then we found a specific member of the family because we had a little piece of information. We knew what point it went through. All we did was sub it in, the x in for x, the y in for y, solve for k, and rewrite your equation. Okay, in example 2, we are going to determine an equation for the family of cubic functions given integral zeros. That just means you have zeros that are not rational, so they don't need to be expressed as a fraction, or they can be expressed as a fraction over 1. So the zeros in this case are given to us. The zeros are -2, 1, and 3. I always kind of work in this kind of list type way. I write the zeros, and then from the zeros you get the factors. The factors here are going to be x plus 2, x minus 1, and x minus 3. Try and think faster than I'm writing, and then you can kind of test how you're doing as well. And now we need an equation, which really means we just take our factors and we put a multiplier k in front. Quite often I'll use the letter a there. The a is very often used as the leading coefficient multiplier. So if you see an a there, it means the same thing, okay? But we're in factored form, not like vertex form or the form of the equation that shows transformations. So k means something different than it would in that form. It doesn't really matter what letter is there. K and A are common ones. Our factors are x plus 2, x minus 1, x minus 3. That's A, an equation for the family of polynomial functions with zeros at -2, 1, and 3. Then write equations for 2 functions that belong to this family. Go ahead and write 2 of your own. Whenever I'm writing my own in my notes, I make sure I do one that's negative and one that's a fraction or a decimal so that I don't get my brain stuck thinking about just common numbers like a multiple of 2 or a multiple of 3. But give yourself something to actually look back at and learn from. Okay, so there's 2 equations. I'm sure yours looks something like that. If not, you can change yours and copy mine. And the last thing we need to do, 2 more things. We're going to determine an equation for the member of the family whose graph has a y-intercept of -15. Now there's a couple different ways that you can do this. One way is that you know that a y-int at, what was it, -15 has a point. It crosses the y-intercept when x is 0, right? So that would be 0, -15. So what you could do is sub in 0 for x everywhere and -15 for y, and then solve for k. Another way to do that would be to say you've got the y-intercept is going to be the product of all of the constants with k. So you could actually multiply all your constants. You'd get +3, +6, and you need 15, -15. So you'd go -15 divided by +6 would give you your multiplier. It's one way to do it. We'll go with the basic way of just inserting 0 and -15. So we've got -15 equals k, our unknown multiplier. And then all of our factors have a 0 for x. 0 plus 2, 0 minus 1, 0 minus 3. And then we can do the algebra on this. Negative 15 equals k times 2 times negative 1 times negative 3. That's negative 15 equals positive 6k. Divide both sides by 6, and you get k equals negative 2.5, which tells us that in this family, the only function with a graph that has a y-intercept at negative 15 is y equals negative 2.5 times our factors, x plus 2, x minus 1, x minus 3. And D asks us to sketch a graph of the functions in part B and in part C. So we're going to do our best to do that. I'm going to clear some space. I'll leave those two functions on there, and the last one we created was negative 2.5 times all that. And actually you can go ahead and mark your x-intercepts. You should have x-intercepts at negative 2, positive 1, and positive 3. We know that the last one we did, I'll do it in blue as we did, it has a y-intercept of negative 15. So maybe here we'll just go 5, 10, 15, 20. So that's negative 15. It looks like it's going to be coming back up. So it'll basically, the minimum point here will split this. And it's negative. It's a negative cubic. So it's coming down here and down there. So we just do our best to sketch something that goes through there. Coming down, we got a y-intercept at negative 15. And it doesn't have a huge stretch factor. We could figure out where this kind of point is. If we know that x is 2 here, you could really just sub in 2 for x. You'd get 4 times 1 is 4, times negative 1 is negative 4, times 2.5, you'd be at positive 10. So you got 10 there, 5. If you do want an accurate sketch, you can do that. Just take your x value where you know you are and plug it into your equation. So this is the last one that we did. This is y equals negative 2.5 x plus 2, x minus 1, x minus 3. Can do this negative 7, 1. Oh, mine are more difficult. The negative 7, 1 is too big. We can change that to a negative 2 or a negative 1 even. Let's just leave it at negative 1. You can try to sketch yours. I'll sketch one more just so you can see how to sketch it again, but it's got the same x-intercept, so I'm going through here, here, here. And then it's negative again, the one that I'm doing. So it's going to be heading down the same direction and down the same direction. I know it's going to be shallower because I'm dealing with a multiple of 1 instead of 2.5. Let's figure out our y-intercept is going to be negative 3 times negative 1. That's positive 3 times 2 is 6. We're looking at positive 6 times the negative is negative 6. So we're down right here. Again, this is going to split the difference. Our local minimum is going to be right around there. You could figure out exactly where that is. But again, you're just doing a shallower curve. It's just a sketch. It's going to look something like that. That's probably enough sketching. You can figure out your own. You can also always double check Desmos to get a better idea of what it should look like. Okay, example 3, determine an equation for a family of quartic functions given irrational zeros. So this time a little more challenging. We have another factor because we're quartic, and our zeros are irrational. So it tells us that the zeros are +1, -1, and 2 plus the square root of 3, and 2 minus the square root of 3. But, yeah, that's good. So we can develop our factors from that. Our factors then would be x minus 1, x plus 1. Don't normally put brackets around it at this step. X minus 1, x plus 1, and then be careful here. It is x minus our factor. So it's x minus, and then you could throw in brackets 2 plus radical 3. And then over here, in the next one, you have x minus 2 minus radical 3. Now I'm going to reduce those, and you'll see what happens. This negative sign has to get distributed to both terms inside that binomial. So you end up with x minus 2 minus radical 3. And in the next one, this negative sign again gets multiplied to both of those terms in the binomial. You end up with x minus 2 plus radical 3. All right, so those are slightly different, but there's all of our factors, and again, we're going to work the same way. So here comes our equation. It looks trickier. We're just going to follow this out. The equation y equals some unknown multiplier k. We have x minus 1, x plus 1, x minus 2 minus radical 3, and x minus 2 plus radical 3. From here, we want to see something, and I'll ask you if you see anything special between these two and between these two. You see anything that we've learned about. Okay, so what we see here is the product of a sum and a difference. Between these two terms, you have x plus 1, x minus 1. So when you multiply them together, that's the product of a sum and a difference. We have the same thing here. Look at what we can do inside these larger brackets. We can actually, and maybe I'll rewrite it so we can see it better. So our first two terms, factors x minus 1, x plus 1. That's easy to see, the product of a sum and a difference. Might be a little bit harder to see here, but I'm going to group these next guys. Not group them, they're going to be separate, but inside, I'm going to create a group inside them. Rather than picturing up here where the 2 plus radical 3 was grouped, instead I'm going to group this 2 with the x. So you have a x minus 2 minus radical 3, close off. And the next one, you group the x minus 2 again, and you have plus radical 3. And if you write it like that, you can really see that you have again the product of a sum and a difference, which means you can rewrite that as the difference of squares. So in order to reduce this, again, the first ones as a difference of squares would be x squared minus 1. And this next two square brackets, they would be x minus 2 squared minus, and when we take, I'll write this step in a way that we can kind of see it step by step. But what happens when you take the square of a square root? You have the square root of 3 squared. You're just going to end right back up at 3. Whatever value is under the radical here, you're going to end up with that. So we can reduce this, and it becomes, we're going to do a couple things at the same, well, I'll rewrite this first. We've got x squared minus 1, and then out here we have x minus 2 squared minus 3. And this is still pretty ugly and messy. What we would really want to do here is get our factors of x together. So the next step would be to expand both of these polynomials, both of these, the binomial here and the binomial here. We're going to expand it all. So we end up in multiplying it together. We're going to first expand this guy. We'll leave x squared minus 1. And then here we have x minus 2 squared. That becomes x squared minus 4x plus 4. And then we still have that minus 3 there. So we can simplify just that second bracket as x squared minus 4x plus 1. And now we can distribute all of this. And we're going to end up with x to the power of 4. So now what I'm doing is distributing this, the binomial to the trinomial here. So we've got x squared times negative 4x, which would be negative 4x cubed. Then we've got x squared times plus 1. So that's going to be positive x squared, but I'm not going to write that because I notice what my next multiple is negative x squared. So the positive x squared and the negative x squared are going to cancel each other out. So I can skip down to negative 1 times negative 4x, which is positive 4x. And negative 1 times positive 1 is negative 1. And this would be a fully reduced family equation that represents the family of polynomial functions with these irrational zeros. Okay, so a few more steps. If you get to here, you have already expressed, you've found an equation for the family of polynomial equations. Okay, even if you're here, you've done it, but you can reduce and simplify. Okay, so the rest of this is reducing it and simplifying it. And even though it had irrational zeros, it actually still only has integer coefficients. So it looked really hard, but it really didn't end up being so hard. All right, part B says determine an equation whose graph passes through the point 218. We're fairly familiar with that. We're just going to sub in the point 2 for x and 18 for y and solve for k. I can probably do it. If I slide my board over, I'll just do it over here. Alright, so now we have 18 equals k times 2 to the power of 4 minus 4 times 2 to the power of 3 plus 4 times 2 minus 1, all in that bracket. We can simplify this bracket. 2 to the power of 4 is 16. 2 to the power of 3 is 8, times 4 is 32, 4 times 2 is 8, minus 1. We've got negative 32 and positive 16, that's negative 16, plus 8 is negative 8, minus 9 is negative 9. So we've got negative 9 k's, divide both sides by negative 9, we end up with k equals negative 2. So, for part B, the member of this family that goes through 218 is y equals negative 2, x to, and then in brackets, x to the power of 4 minus 4x cubed plus 4x minus 1. Okay, with our math skills that we have now, we can really determine the equation. When we're given a graph, you can figure out the equation as long as you know it's zeros. So we're going to follow all the exact same steps. We're going to follow the get the zeros, get the factors, get an equation for the family of polynomials, and then we're going to choose one point that we can see from the graph other than the zeros themselves to be the determining factor for helping us solve for k. So from the graph, what are the x-intercepts? -3, -1/2, +1, +2. From that, we can get our corresponding factors. Factors are x plus 3. In this one, so you'd be very tempted to write x plus 1/2, okay? But from our factor theorem and from other things, we understand that when the 0 is rational number, it's b over a. So what you end up with here is 2x plus 1. Okay, and you can double check that by thinking back what happens if I put -1/2 in here. I get 2 times -1/2, which is -1, plus 1, that's 0. Okay, so this is a match. Remember to do it that way. Other factors, x minus 1 and x minus 2. So our equation then, again, I'm doing this for the sake of notes. You don't necessarily need to write this every single time on the left, but our equation is y equals some multiplier times x plus 3 times 2x plus 1 times x minus 1 times x minus 2. Look at the graph, pick a point that it goes through. Can you see any point that it exactly goes through? At x equals -1, it goes through a nice point. By looking at the graph, the function includes -1 and what y value? -1, -6. So sub x equals -1 and y equals -6 to find k. So we have -6 equals k times -1 plus 3 times 2 times -1 plus 1 times -1 minus 1 times -1 minus 2. If I were doing this in my practice problems, I'd do all those in my head, and I'd skip down to this next step, which we end up with a first bracket, a multiplier of +2, then -2 plus 1, which is -1, then -1 minus 1, which is -2, then -1 minus 2, which is -3. Multiply those together, 3 times 2 times 2. That's 12. We have 3 negative factors, so we end up with a negative, so that's -6 equals -12k. Divide both sides by -12. K equals 1/2, or 0.5. Therefore, the function shown in the graph, y equals 0.5 times x plus 3 times 2x plus 1 times x minus 1 times x minus 2. Finito. Practice problems come from page 119, sorry. Numbers 1 through 10 and 14 through 17.